Afternoon. I'm really pleased to welcome Jordan Boyd-Graber here this afternoon. Jordan graduated around the same time I did. He was at Princeton working with David Bly, doing some really interesting things with topic models. He then came to the DC area to do a postdoc at the University of Maryland, and we were incredibly happy to decide to stay. He's now an assistant professor at the I School at the University of Maryland, so we're incredibly lucky to have him in the area. And he has now assembled a formidable group doing really cool things with topic models. And one thing that sets apart his work is he actually gets people to use his models, which is a crazy idea. It took us a while before we started trying these things with topic models. But it means that he's got really interesting research about what actually works and what doesn't work and what people actually want to see. And so I'm really happy that he's here to talk to us about it.
And I'm very glad to be here. So before I get started, I just want to say, please do interrupt me during the talk. So if you have questions or comments or things you want to interject, please do interrupt. And I'll pause to encourage that, so please take advantage of it so I don't look foolish when I pause. OK, so today I'm going to be talking about topic models and when they go bad. And so my talk is broken up into 3 parts. First, I'll give a perhaps unnecessary introduction to topic models. A lot of people here are doing great work on topic models, but just in case, I'll go through that. Then I'll talk about all the lies that you've been told about topic models and where they actually fall down. Then I'll talk about some stuff, how we can correct these problems to make topic models actually fit for human consumption. OK, first, why topic models? So a common use case for topic models is that you have a large collection of documents, say like a decade worth of newspaper articles, and you don't have time to read them to get a full idea of what's going on. And topic models are a way that people can get a fairly high-level view of what's going on in a corpus without doing the actual reading. And the nice thing about topic models is that they're unsupervised, that you don't need to have any manual annotation. You just throw data at it, and it more or less works. And just sort of pictorially, what you get as input are a bunch of documents, just the words in those documents. And then as output, after you put in that input, you get a bunch of topics, which is why these are called topic models. And topic models are basically just a bunch of words that seem to coalesce around a common theme. And so, for example, if you throw in the New York Times articles from the 90s, you get things that look like this. So you get one topic about technology, topic number 1, one topic about business, topic number 2, and one topic about the arts, topic number 3. So this is one part of your output, but that's not all you get from a topic model. You also get an association between these topics and the documents in your corpus. And we can represent it by something that looks like a triangle. And so in the corner here, you have topic number 1, red light, green light, a 2-tone LED to simplify screens. This is a document entirely about the technology topic, which is why it's in that top left corner. And then as you move over to the right, you get documents that express more and more of topic number 2, like stock trades, a better deal for investors isn't simple, is all about business. In between, you have something like the 3 big internet portals begin to distinguish among themselves as shopping malls, which is a mixture of technology and business. And then as you move down in the simplex towards the center, you get a mixture of all 3 topics. And this is a good point to mention that although this is an unsupervised model, the models that I'll be talking about today assume that before you do anything, you specify the number of topics that you want to find, and it does the best job that it can to find those topics. So questions thus far about the inputs and outputs of a topic model. OK. So topic models, just to recap, give you 2 outputs, a connection between topics and words, and a connection between documents and topics. And both of these are just multinomial distributions. And because we're using the language of probability to express these things, we can use statistical inference to figure out what these things are given a set of data. And that these topics make sense, that it makes sense to call them topics, is because of the way that words are used in a natural language. And in this talk, we'll be mostly focusing on latent Dirichlet allocation, which is a fully Bayesian version of PLSI. But there are many different topic models under many different names. OK, so any questions so far? OK. And so I should also mention that there are applications beyond text. You can use topic models with other conceptions of documents and words. I'm not going to talk about them, but this sort of adds to some of the momentum that topic models have had. If you consider passages to be your document in a music score, you can get state-of-the-art performance on key signature detection. You can use it for image categorization. You can use it to infer stuff about social networks. And so this is all neat, and a lot of the things I talk about here can also be applied to that, but I won't be talking about it. OK, so that's what topic models are. And now I'm going to talk about why topic models sometimes suck, and the process that people use sometimes to lie about topic models that I call reading tea leaves. OK, so we've talked about what topic models are, but how do you actually evaluate topic models? So typically, what people have done in the literature is you have a corpus, you fit a bunch of models, and then you compute the held-out log likelihood on held-out data. And so this held-out log likelihood, or perplexity, gives you a measure of the predictive power, but it doesn't really measure what the topics are. And so this is a little bit odd, because if you look at a topic modeling paper, it does seem that people care about what the underlying topics are. And so if you look at a topic modeling paper, you're going to see a chart that looks like this or this. And this seems to show that people care, or at least think these things are cool. They actually want to have good underlying topics in their model. And this is true even if you're not using English. It's true even if you're not using natural language. And this is so powerful that people even use the topics that you discover in this unsupervised way to draw conclusions, such as a conclusion in this paper that statistics is taking over computational linguistics. And they were able to make this assertion because people cared and understood and were able to believe that these topics make sense. And this goes even beyond academia. People have used topic models in search engines in order for people to figure out what they're interested in and also to refine queries. But this is a little bit odd, because this is not how we evaluate topic models at all. And really what's happening in these charts that I've showed you is a process that we like to call reading tea leaves. You stare at it long enough and it makes sense. And how we evaluate doesn't measure this. How we evaluate just measures the predictive power. And so in this part of the talk, I'm going to propose a direct quantitative human evaluation of whether these things make sense. We're going to test this measure of interpretability, how much it makes sense, on a bunch of different models and corpora. And we'll show that there is a disconnect with likelihood. And so it turns out that what we care about and what we're measuring aren't necessarily aligned. And it's appropriate that I'm giving this talk here, because when I first gave a talk at Hopkins, right when I was finishing my PhD, I was giving a talk with a fancy topic model, and I was giving one perplexity evaluation after another, and Fred Jelinek asked, well, you have all these nice perplexity numbers, but do you have any real results? And so that's appropriate for a number of reasons, and so this is sort of my answer to that question 3 years later. Here are some real results that go beyond just measuring perplexity. And it turns out that what you care about doesn't necessarily match with perplexity. OK, so questions so far? OK, all right, so.
What do you say that you care about?
OK, yeah, so what we care about is interpretability. Do these topics make sense? Does the underlying semantic, or let's not go that far. Does the underlying latent space actually make sense? So do the charts that you see like this actually make sense to a human being? Exactly, yes. Right, or at least dancing around it. Okay, other questions? Okay, all right, so how do we do this? And so interpretability is a human judgment. And so we're just going to ask people directly. There's no getting around that. But we want to do it in a way that's quick, that you can relatively easily assess how good a model is, that's relatively fun. It's not too onerous a task for a human being to do it, and that gives you consistent results. So what we're going to do is turn to Amazon Mechanical Turk, something that you guys know a whole lot about here, and develop two tasks that we're going to call word intrusion and topic intrusion to measure how much these topics make sense. Okay, so task number 1, word intrusion. So recall that a topic model gives you output that looks like this. And these are basically just a distribution over words, and hopefully they make some sort of sense. And so what we're going to do is we're going to take a topic, say, that our model discovered. So this is a pretend topic here that has dog, horse, pig, and cow. And so our hypothesis is these words make sense together. And if you put a word that doesn't belong, say a high probability word from another topic, and stick it in there, if the original topic made sense, people will be able to detect the new thing that you stuck in there. And we call this the intruder, the topic intruder. And so this is a word that is hiding in the topic. And we'll just ask people to click on the word that doesn't belong. And our hypothesis is if the topic makes sense, people will be able to pick out the word intruder consistently. Okay, questions on how this task is set up?
And how do you select the intruder? Is it just
So it's a high probability.
vocabulary?
No, so that actually doesn't work so well because then people will just,
It gets really easy.
yeah, so people will click on the word that has low probability. So we're using a high probability word from another topic. And so this is a word that has relatively high probability in some other topic. So it's about something else, or so says our model.
So when you say high probability, are we looking at the top 100 words in each topic, the top 10 words? Like sort of, it seems like we're evaluating the very top.
Right, yes. And perhaps that's the wrong thing to do. But yes, we are using the top 30 words. And so, and that's typically what people show in these papers. And so that's what we're doing again. Good questions. Other questions?
Kind of reminds me of questions that have been too long to remember, like an SAT question or some intelligence test question, kids' comics page. Yeah, Sesame Street. That's
Yeah, one of these things is not like the other. Yeah. Right. So that's the goal. But so unlike this, there's no correct answer. And so we just want to know if the model is putting things in appropriate sets. Okay. So this is what the task looks like. Each of these is a topic with an intruder inside, and we ask the person to click on the answer. And so they can click on the answer. We shuffled the order of words, which intruder we used was, again, varied. And we just measured how often users clicked on the intruder. And we called this model precision. OK, so that was task number 1. Any questions on task number 1? Yep.
So if you had a topic that was already sort of okay, but had something you might want to call an intruder, so presumably then the subjects would be equally likely to pick your intruder or the one that was already there that you to.
Right. Well, so in that case, you'll have a lower precision, that there was a word that didn't belong in the original topic.
I guess what I'm suggesting is maybe the rest of the topic would be coherent.
Yeah, exactly. And so there are different things you can do. You could have a more complicated measurement of what people clicked on to see how confused they were. But just to keep things simple, we just how often did they click on the intruder word? And we'll see an example of a more extreme case where people always clicked on a word that was actually in the topic, but they thought the intruder fit better no matter what the intruder was. Okay, so moving on to task number 2. And so this is measuring the association of documents to topics. And so this is how well each document gets associated with a set of topics. And so here what we did is we displayed the document title and the first 500 characters in the document to users. We showed 3 topics with the highest probability for that document. And then we choose one topic randomly. And then we ask the user to click on the topic. And so by here, topic we mean a collection of words. Have them click on the topic that is out of place. So this is like what we were doing before, except now they're looking for an intruding topic rather than an intruding word. And again, our hypothesis is if that the association of topics to a document is interpretable, users will consistently choose the true intruding topic. And so this is what this task looked like. So you have the title of the document, the first 500 words, and they have to click on one of these rows of words to say it doesn't belong, like so. OK, so those are our 2 tasks. Any questions on task number 2? Yep.
When you picked your intrusion topic, was it like one that was definitely a low probability for that document, so it doesn't like maybe show up later? Or?
Right. So not exactly. So we chose it at random, but we have a way of measuring it that sort of accounts for that. And I'll get to that in a second.
Can we look at the previous slide?
Oh, yeah. Mm-hmm.
Which row is the bad row?
Right. So in this case, I believe the bad row.
The second row.
Right. Well, so what do you guys think?
Third seems kind
The first 2 don't.
Yeah, so actually, this is the true intruding topic. So this is a restaurant review. And so this makes sense. And this really has high probability. And so these also sort of make sense, but not really. You have table and you have weight. And this should actually be head waiter. This should be a bigram. So that's one problem with these sorts of models. So both of these have relatively low probability. And so the way that we score it, getting back to your question as well, is we basically look at the log odds between the thing that they clicked on and the true probability. And so the higher the probability of the thing that they clicked on, the lower the score of this model.
And sorry, you probably said this, but the users like the top 8 words in the topic,
Mm-hmm.
or the top 8 words in the topic and also in the document?
No, so it's just the topic. So we're not doing an intersection of the 2. Yeah, yeah. OK. All right, so what we did is we tried this out on 3 different topic models. And so I won't get into the details of these models. And so basically, there are 3 different models here going from old and simple to new and complicated. And so PLSI is a relatively unconstrained model. Latent Dirichlet allocation makes different assumptions about the per document distribution over topics. And the correlated topic model makes even more complicated assumptions about the per document distribution over topics. And so basically, old and simple to new and shiny and complicated as you go down. And we applied this to 2 different corpora, a subset of Wikipedia and the New York Times corpus released by the LDC. So we chose these because they're well structured. So each document sort of begins with a summary paragraph just by the conventions of Wikipedia and newspaper articles. They're both real-world corpora. They're read by millions of people every day. And they evince a lot of different themes. So we should hopefully have some sort of interesting structure that we can tease out with these models. OK, so what we did is we fit these 3 models to both corpora. Each model had 50, 100, or 150 topics. We looked at 50 topics from each condition, presented them to 8 topics, and did task number 1 with that, the word intrusion task. And we did 100 documents from each condition, presented to 8 workers for the topic intrusion task. So questions on the experiments or data? OK. OK, so now we finally have the ability to answer the question, which topics make sense. And we're able to measure the model precision of each of these topics. And so for LDA, on 50 topics, a lot of the topics seem to make sense. So they're all the way over on the right. People are clicking on the true intruder. That's good. As you move over to the left, the topics make less sense. And over on the far left, you have a topic where you have this word taxis that people thought fit so badly that no matter what the intruder word was, they clicked on taxis instead. And so perhaps this made sense within this corpus, and it improved held out perplexity, but in terms of making sense to a human being, it didn't. And so we can do the same thing with the document associations to topics. Which ones made sense? And so, so this is the topic log odds. And so this is basically what is the probability of the intruding topic that they clicked on. If it's a low probability, that's good. If it's a high probability, that's bad. So bad is to the left, good is to the right. And so basically, if you look at Wikipedia documents, documents like Lindy Hop are about dance and nothing but dance, and the model was able to correctly choose that, and people were able to click on low probability topics that were associated with that document. As you move to the left, you get things like book, which doesn't really have a clear topical representation in this model, and people were totally confused about which topics did belong and which didn't belong. And so these were basically a bad association of topics to documents. So questions so far? Yep. So the y-axis is so this is a histogram of the score, and so some documents were perfect, and then most documents were in this middling territory, and then you had some things at the tail. So this is just the number of documents that of the ones that we looked at. Other questions? Yep.
So in this test, the way you set it up, you only show the first paragraph essentially.
First 500 words, yeah.
Some sort of a summary, but I can see that for something like an editorial, maybe you start talking about one thing and then.
Right, that's fair enough, and so that's sort of why we did exclude editorials, but yeah, so that's part of the reason why we chose these data, because hopefully the first paragraph, first couple of words would give you a good sense of what it's about, so that people could be able to pick up on that. But good point.
So I just wonder if with some of these bad performing documents, if we were to give them another part of the document rather than the results.
Right. So of the things that we looked at, it didn't look like that. That didn't seem to be. But I think that would be more true for other corpora.
Or you could also just use the first part of the document when you throw in the document.
Right. The problem with doing that is then you get more entropic associations to topics. And so we wanted it to be as real life as possible. So yeah, so there are trade-offs here. But good point. Okay. All right, so and now we can go the next step and compare these results to what you get if you do the traditional evaluation. And you can see that in 3 of the 6 cases, the new, shiny, complicated, correlated topic model does the best, as you would expect. And we can also compare it to what we're getting in terms of the human metrics. So here, if you look at the association of the likelihood to these to model precision, so this is looking for the word intruder, you can see that within a model, so let's say I have LDA, I want to choose the number of topics. As you increase the number of topics, as you expect, the likelihood improves as you go from left to right. But as you do that, as you increase the number of topics, the model precision seems to be going down. And so for these 2 guys, the slope negative is significant at a 0.1 level, and here at a 0.5 level. 0.01 level and a 0.05 level. And so it does seem that as you increase the number of topics, people like it less and less, even though the likelihood is going up. And the same thing is true if you compare across models. So you want to decide, hey, should I use LDA? Should I use PLSI? Should I use correlated topic model? And here, if you look at the topic log odds, LDA and PLSI are doing pretty well on the topic log odds. People are clicking on low probability topics when you put in a topic intruder. The correlated topic model isn't doing so well, but it's way out in the lead in terms of the held out log likelihood. So even across models, it doesn't seem to be the case that likelihood is giving you what you want if you want interpretable topics. Okay, so to wrap up the second part of the talk, we showed that there was a disconnect between evaluation and use. So people traditionally, when they evaluate topic models, use something like held out log likelihood or perplexity. And in the case where you want to have these topics for human consumption, that isn't necessarily the right thing to do. And for topic models, even though it's an unsupervised method, there are ways that you can make direct measurements of how useful they are, or how interpretable, at least, they are to human beings. And at least to me, this is a surprising relationship between the interpretability of the model and the likelihood. And so I think the takeaway of this is that measure what you care about. If you care about likelihood, if you're doing a prediction task, then sure, perplexity, likelihood is great. But if you're doing something as an aid to visualizing large corpora or to understanding what's going on in a data set, then maybe that isn't the metric you should be using. Okay, so questions? Yep?
A few slides back, you compared the two more that.
Yeah.
You found out likelihood. It's not so convincing even that CTM does better. It does better half the time. It does worse half the time.
Right, so it's easier to see on these charts. And so for example, so in this case, it's more pronounced. So this is on Wikipedia that here you compare to this, to this, to this, this to this to this. It does seem to be winning. And if you look at the correlated topic model paper, they show this in a lot more detail, that they win a lot when you compare against other papers.
The measures that we care about, they're losing by a significant margin.
Exactly, yes.
And the other models are computationally simple, and they take much less time to train as well.
Exactly, yeah.
So they're better in every way that you care about.
I won't go that far.
There's
Yep.
one issue though, which is that you're comparing likelihood and the model with different numbers of parameters.
Yes.
Gives me a bit of
Right, indeed. And so,
so in other words, I don't read anything in the fact that, for example, the red triangle is to the right of the blue green. It has more parameters, so I would be surprised if it were.
right, yeah.
Just because it's to the right doesn't tell me that I should believe anything.
Right.
I don't know what to think about the goodness under this other measure.
Yeah, so that's fair enough. So we tried to make these as comparable as possible. And so if between the correlated topic model and LDA, if you consider the number of parameters, the number of topics, which isn't the right way to do it, then they match on that front. And so so yes, you're absolutely right. But if you're putting it in an interface, they would look the same way to people. So if you're having sort of a human-centric evaluation, then this is the best way to do apples to apples.
I know. All I'm saying is I don't want people to read too much into this.
Oh, yeah, indeed. Right. And right, if you want the straight perplexity comparison between correlated topic model and these other papers, you should read the correlated topic models paper, which does it in a much more principled way. Yep.
With respect to the number of topics and your evaluation strategy, it kind of makes sense to me that the more topics there are, the finer grain they'll be. And your metric is sort of like precision-like metric.
Yeah.
It would be easier to determine an outlier if you're looking at coarse ideas rather than fine grain ideas.
Indeed, yeah.
Have you thought about expanding that to kind of have the inverse of that, some sort of a recall?
Right, and so that's a lot harder because then you can't you have to ask people what's missing rather than what doesn't belong. And so we have sort of done that in a very qualitative way, and I'll talk a little bit about that later. Yep.
So this interpretability kind of set of measures that you're covering, they seem really aimed to like the story of topic models, right?
Mm-hmm.
Like contiguous peer topics that you can put together to build documents and describe them accurately.
Mm-hmm.
But I don't know if that necessarily like fit. I mean, I'm trying to attack this and say like, does it really interpretability when you're talking about the use of topic models being like searching
Mm-hmm.
or helping someone to read a vast corpus quickly? So I'm just curious if you know like how to like if you have like example of talking about people trying to search something. I understand it's a little more complicated. I'm not sold on it.
Right, and that's fair enough, and that really is the next step. And so no, we haven't looked at that in any quantitative way. However, qualitatively, I can say that when people look at a topic model and they see a junk topic, something that doesn't make sense to them, they get turned off, and they say, well, I don't really trust anything now that I've seen this.
I'm thinking about like the topic parity thing. Like
Mm-hmm.
one intruder word in the topic, if you're trying to search might not throw you off.
Right.
Find the most likely word and try to pick that and then use the topic as a related space.
Right, exactly. And so, but if you have a junk topic and people can't tell what the intruder is, this will detect that. And so it's not just detecting single words that are going in. It can also detect junk topics where just it's a completely random set of words and people just click randomly. And so it also detects that. And that is a real problem that people have in practice. Yep. Okay. Other questions? Okay. So moving on to what you can do about these problems, how you can fix them. And this is a setup for doing interactive topic modeling where you're able to actually put the knowledge that you get from humans back into the system. And so why make this interactive? One, you can correct obvious errors easily. So humans are really good at detecting problems, and they can tell you what's wrong. And usually, these problems are simple enough that you can fix it. It builds better intuitions of the model for people who are using it. So if they're able to look at a model, change it in a way that makes sense to them, using semantics that you've given them, they have a better sense of what's going on under the hood. And it gives you better buy-in. People are able to trust the models if they can tweak it to make it look like something that matches their intuitions. And hopefully this would allow you to build better downstream models if you're using topic models for prediction, say, like Mark is doing, or any other application. If these models make more sense a priori, anything you do downstream should hopefully improve. Okay, so what are the problems that people observe in topic models? We've talked a little bit about this, but so there are two sort of problems that we'll try to address here. One is that you have, say, two topics like this, where words aren't together, but they should be. And so if you show this to people, they say, oh, NASA shuttle and launch should really be together. They're in separate topics, but they should really be in the same topic. Another problem, and this is on real data, so we've been working with people at the NIH, and so this is a topic that comes out if you do topic modeling on all of the NIH abstracts and publications that came out of that research. And if you show this to someone at the NIH, they say, well, there's really something about bladder and urinary stuff going on in here. But there's also something about spinal cord injury and stuff going on in your spine, and those things don't belong together. And they get really upset about this. I mean, so they reject the entire model when they see something like this because these are in different directorates. Yeah, and so this is just anathema to them, and they don't trust any part of the model. Yep.
So, this is a question that I had when I heard David Blumrow talk about this talk previously. When you display this topic, is it from one sample of the given sample?
Right. So this is even better than that. This is averaged across multiple chains, and so this is multiple samples from multiple chains, and so this isn't just a fluke.
Okay. I still want to know if you were to, what's the posture or probability that bladder and spinal cord end up together?
Pretty high, actually, because and there are complicated reasons why that happens, but it's actually pretty high. Yep.
It's because people with spinal cord injuries have better bladder control issues.
Yes, that's absolutely true, and there are a number of documents that talk about this, and right, yeah.
So it sounds like a good topic.
Right, and this is a subjective thing, and so whenever you get humans involved, you are going to have some level of subjectivity, but. Yeah, fair enough. Yeah, and when you're talking about funding, at least at NIH, they like to keep a Chinese wall between these two things.
Well, maybe you should just run it on NIH grant proposals.
Right. Well, they do. Well, no. I mean, that's actually what happened, and so even so, yeah. So people working on one write about the other, even though they're not funded for the other. So, yep.
Does NIH mainly come up with better retrieval models for documents or better topic?
Right. Well, so what they want to do is understand their corpus, but they want to understand it in a way that doesn't conflict with their prior notions. So. Exactly. Yeah.
So let me see if I can make a more charitable view. They want what the model to 95% of what the model tells them to be stuff they already do, so they trust it.
Mm-hmm.
And so they trust that the other 5% that they don't know is actually correct, even though they didn't know it.
Exactly. Yeah. And maybe that percentage is a different number, but yeah, that's a good way of putting it. Okay. All right. So those are the problems. How do we fix it? And so normally in a topic model, a topic is just a distribution over words, and they're uncorrelated. And so what we can do is we can add in correlations to this uncorrelated model to fix these problems. And so the problem here is that topic models normally are uncorrelated. And so the advice that you get can be encoded as correlations. And so positive correlations among things that should be together, and negative correlations between things that should not be together. So put a negative correlation between spinal cord and bladder, and put a positive correlation between Constitution and President, NASA, Space, and Shuttle. And so the technical details of this is you use a Dirichlet forest, which is basically cascading a bunch of Dirichlet distributions together. I'll talk a little bit more about that in a bit. Okay. Actually, I'll talk about it right now. So in LDA, a topic is a multinomial distribution over words. Here we're going to model the topic as a tree. So you start at the root of the tree, you work your way down, choosing each path from a multinomial distribution until you hit a leaf node, and by construction, leaf nodes are words. And so that's the generative process for the topics. And we can encode these correlations in this structure. And the nice thing about doing it this way, as opposed to using like a normal distribution and then renormalizing it, this is still conjugate, so inference is still pretty easy. So questions so far? Okay, so this is what a normal uncorrelated distribution would look like. You have one root. You all have the same prior to get to any of the children. What we're going to do instead is when we have a negative constraint, put those under the same parent node and make that Dirichlet prior to be very, very small, and this encourages sparse distributions. And so you start at the root node, you come down to this guy, and whenever you get to this guy, you have a stark choice to make, either go here or here. You can't do both in a single topic. And similarly for positive correlations, you put those under the same parent. And when you have a positive correlation, you have a parameter that's a lot bigger than you would have normally. And then you start at the root node. Well, let's go over here for equity. You start at the root node, then you come down here. And when you get here, the prior encourages you to choose any one of these words. It doesn't really matter which one. They're all going to have fairly uniform probability. And so this encourages a positive correlation. So questions on this? Okay. All right, and so there are some tricky details that I'm not going to talk about. If you have overlapping correlations, that has some problems. And so are positive correlations transitive? If you say yes, then that makes things a little bit similar. If you say no, then that means in one interpretation that you have multiple senses of the word. Negative correlations require some tricky graph computations to find the complement graphs and consider all possible universes where they aren't stuck together. And another tricky question is how do you do hyperparameter optimization in a way that doesn't undo what you're trying to do? And I'm just going to sweep those under the rug for now, but I wanted to bring them up. Okay, so we have these models. How do you incorporate this feedback using the formalism that we just described? So you can do an initial topic model using an unconstrained prior, just a uniform prior distribution like you would normally, get some feedback from a user, and then incrementally relearn the model. And so what we're going to do is replace the old model with a new model, doing some bookkeeping to keep things consistent, and allow us to have fairly fast updating once this happens. And so we're going to do this by selectively forgetting stuff. And this allows us to keep things fast and consistent. And so at this point, you may say, well, why not just start over? And so there are a couple of reasons why you wouldn't want to do that. One is that makes the computation a lot more expensive. And so the user saw your model. The user found some rough edges. And you don't necessarily want to just tear everything down and start from scratch. Starting over might create new problems. So the user found some rough edges in one part of the space, but they were perfectly happy with everything going on over here. Why do you want to change that? And it's also a bad user experience. If the user invested a lot of energy to understand the model, and they learned, oh, topic 47, that's about politics, and then you blow everything up and start over, there might well be a politics topic, but who knows where it's going to be. And so it throws away the time that the user spent understanding the model and building a mental picture of what's going on. And so what we're going to do is we're going to view the problem as one of online inference. And so the suggestions that you receive from the user reflect errors in the model. And what we're going to do is we're going to forget all the places where the user saw problems. And then we're going to pretend that we're seeing it for the first time. And so this allows the changes in the model to be reflected during the inference process. So questions on the setup?
I don't understand what you mean by pretend you're seeing it for the first time, because if you pretend you see it for the first time, you have all the properties that you want to avoid it.
Right, but it's different because the underlying model has now changed. We've replaced that symmetric prior with a model that has constraints that should hopefully bias you away from the problems that you observed before.
But you're still guaranteed that topic 47 will still be politics?
You're not guaranteed, but it's much, much more likely than if you started from scratch. Okay. All right, so I'm sort of running short on time, so I'm going to skip over a little bit of this. This is basically a review of Gibbs sampling. And so this is a toy data set that has all the examples, has all the problems that the example topics that I showed you before. So you'll notice that bladder and spine are in the same topic, and so we're using the colors to denote the topic assignment. And you'll also note that NASA is not linked together with shuttle. And so these are the same problems that we had in the example problems. Okay, so let's say that we want to induce a negative correlation. So idea number one is to selectively forget terms. And so what we're going to do when we forget terms is we're going to pretend that we don't have any topic assignments for these guys, the terms that people pointed out problems with, and then run inference forward. And so what happens then, you need to choose a topic for this guy. And let's say you chose the yellow topic. And so that means, because you want to have consistent topics within a document, that when you get to bladder, you're more likely to have the yellow topic there. But when you get to spine, this was red before, but now you have this, you don't want this to be yellow, and now you have the constraint that says, hey, don't put bladder and spine together in a topic. And when you have a negative correlation, you can't have both bladder and spine appearing in the same topic, so this has to become another topic. Let's say it becomes green. So that fixes the problem. So that was one scheme for forgetting selectively. Another scheme for forgetting is basically throwing away any documents that had the terms that showed problems. And so this is what that looks like. So let's say that we wanted to introduce a positive correlation between shuttle and NASA. And so now when you run inference forward, you need to choose a topic for NASA. Let's say that that becomes blue. Similarly for shuttle. Similarly for launch. And now when you get to the second document, even though NASA and shuttle wanted to be in the same topic because you now have this positive correlation, there's nothing keeping you from using a red topic over here because the positive correlation can appear in multiple documents. Okay, and so just as a qualitative example of what's going on, let's say that you fit a topic model to the New York Times documents from the 1990s. And so what we have here is we have one topic about Russia, and we have one topic about the Soviet Union. And you might say these are part of the same historical continuity. They should really be in the same topic. And so you can introduce a constraint that puts these words together in a positive correlation. And so afterwards, what happens is you now have all of the Russia stuff grouped together in topic 20. So this is using the document forgetting scheme. And if you look at topic 1, which was about Russia before, it's now about democratic movements in countries other than Russia. And so this is sort of getting what you want. You subtracted Russia out of what was topic 1 before. At the same time, all of the other topics have basically stayed the same, more or less. There have been slight tweaks, but the overall gist is the same. Okay, so the next thing we did is we wanted to simulate an interactive user. And so here we used the 20 newsgroup data set to simulate a user that had some sort of preconceived notions of what the topics should be. And they're going to build up these constraints one word at a time. And so we use this by extracting the information gained from each of the 20 newsgroups in the 20 newsgroups corpus. And we're going to add them one by one to the model as a positive correlation. And so after that, we're going to train a classifier on the topic model document features in order to predict the category of each document. And so the idea here is if the model is doing a better job of capturing the underlying topics as expressed by these constraints, the classification accuracy will be better. And we're actually going to measure the error, so the error will be lower. And so this is what that looks like. And so this is evaluating both doing nothing, so that's the none strategy, null, which is starting over from scratch, and imposing these constraints, using the document forgetting strategy, and using the term forgetting strategy. And the document forgetting strategy in red seems to do better than both starting from scratch, forgetting just the terms, or doing nothing, not imposing any constraints whatsoever. So this seems to show that we're getting some sort of gain in this interactive process. And so we also wanted to put these in the wild. And so what we did is we created a mechanical Turk task and asked people to just look at this and to go crazy, do whatever they want. And so this is more of an exploratory thing, just to see what people will do when confronted with this sort of model and these sorts of options for interaction. And so we allowed them to create constraints by clicking on words that appeared in topics. This is what we talked about before. They can add words, they can delete constraints, and all of these things get updated and then redisplayed to users. And I'll skip that since we're running out of time. And what's more interesting is what people did. And so this shows that although some people were able to create good topics that made sense, a lot of people did things that were sort of inscrutable. So, for example, a lot of people put together words that really didn't make sense together. And what was more interesting is a lot of people put together collocations, even though these collocations didn't necessarily make sense given the topics that were extracted. So, for example, Jesus Christ makes sense as a collocation, but even number really doesn't for New York Times documents, which is the data set we were using in addition to 20 news groups. Other topics that were formed were common instances. So like people put together all first names into a topic, which really doesn't make sense because all first names aren't likely to co-occur that much. But this was able to pick out obituary topics. And so that was a neat thing that sort of happened by people playing around with it. And so there wasn't originally an obituary topic, but somebody did this and created an obituary topic. And so another neat thing is that not all of the attempts to shape the topics were successful. So in the 20 news group data set, there's a news group for Mac topics and a news group for Windows topics. And so people tried to put these together a lot. And so they formed a positive constraint between these two things. And the model said, no, 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 I can do much better if I separate these two things out. They're not like each other at all, at least when the 20 news groups data set was collected. So this is showing that the model still has some agency in order to say what actually makes sense in the data. Yep?
Did the constraints that people added ever improve the complexity? Did it ever help correct the search error?
Right. So I will say no with an asterisk. In one case, it actually happened, but that was someone who actually wrote a script to scam us, and so it's unclear what was going on there. So no.
That's for a script and for a search.
Right. Well, it looks like he was using a language model to generate these words, and so it was a pretty sophisticated script. So there might be a paper there. I don't know.
The IP address was not released.
Okay, and so to wrap up the third and last part, what we'd like to do is to speed this up a little bit. Because it's conjugate, it's still fairly fast, but because it's interactive, every second really counts. And so we would like to be able to make this interactive system as interactive as possible. We'd also like to help guide users to find correlations that would help them do what they want. And so this is something that we've been looking at recently by using PMI and other measures that people like Dave Newman have suggested for topic purity. We'd also like to incorporate other domain knowledge. And so we're starting from a symmetric prior, but there's no reason to start from there. You could start from things like gene ontology or WordNet or other sources of metadata that are out there in the wild that sort of guide your topics in the direction you want to go in the first place. Another problem is that the vocabulary of topic models really changes what you see. So it would be nice to have an interactive component to the vocabulary in addition to the modeling. I think this would be really great to form bigrams or to delete words. I think that's really low-hanging fruit that would be nice to see. It would also be great to try this in other domains, like for vision or music or other things where there's still this notion of interpretability in a topic, but maybe the semantics would be different somehow. And then also incorporating this analysis into downstream models. Okay. And so in conclusion, we talked about ways that topic models failed, how to fix them, and created tools to do that. But we would like to do this on more data sets with more things. So if you have any neat ideas, please talk to me. And I'll thank people who gave us help in coding, help in data, and money. So thank you very much. Right, so, yeah.
So it seems really interesting, like the particular thing you said right there is that people want to create a topic, like if you just let them create whatever they want, they create a topic with first name, which is very sensible from the point of view to take a random person and say, here, make a topic for me, but very stupid from the point of view, I want to maximize the likelihood.
Right.
So I'm wondering if there was any option, if you ever thought about like, what's the word, like when you give someone a number before they buy wine, prime them.
Yeah, yeah.
The topic is, so do you give them examples of it before having them run?
Right. So we haven't done any systematic anchoring experiments, but we did give them one example of I think it was lawyer and court. So that was our one example. So we didn't do it in any systematic way. Yep.
This feels a little bit like in statistics there's sort of a real difference between clustering and, say, regression.
Mm-hmm. Yeah.
So in regression, we can really talk about questions like, prediction error,
Mm-hmm. Right.
especially like interpolation, extrapolation, and so on. In clustering, the point doesn't seem to be predicting anything.
Mm-hmm.
The point is that the clusters you get back are supposed to be somehow interpretable.
Right. Yeah.
And that makes clustering a much softer topic than regression. And the statisticians get kind of uncomfortable with it.
Right. Yeah.
I think what you're maybe concluding is that prediction can't be the right test for topic modeling.
Right. Yeah. I would totally agree, and I think the connection with clustering is right on in that this is more of a soft clustering, but it is very much along the same lines. Yeah, so it would be nice if we had something that looked more like regression. And so what is that thing? Yep.
I was wondering if you could debug the question of what human subjects are doing when they do some variant of the task of looking at some words and figuring out if it makes sense. Maybe from more psychology.
Yeah, no, I haven't, and I'm the wrong person to be asking that. It would be nice. So like we tried to correlate with like semantic relatedness and try to find correlations in WordNet and other things to sort of try to make a human in a box. And so none of the stuff really worked so well. But if you have ideas, I'd love to hear them. Yeah. Okay. Yeah.
I mean, there's this. The word of the task very much of this work in use on concept association.
Yeah, and so right, and so we tried correlating. There's a huge database of that from Florida, and we tried correlating against that, and that didn't work either. So I don't know. Yeah.
But that's maybe interesting.
Yeah. Right. Yep.
So it wasn't clear to me in the end how the performance of the interactively learned topics compared to the simple ones that did better.
Right. So that was entirely comparing against LDA, which did in the same ballpark as PLSI, and so we were using LDA just because it's easier to get code for that. So that's an interesting question, but one we haven't really looked at. Yep.
The human evaluation of the human tweaked clusters?
Yes, but it's not in slides yet, and so it does seem to go up, but only for certain Turkers. So right, so that's problematic. We need to have some sort of better control over who we're letting at the system, and so we're doing a case study now with the NIH people, and we'll do the same human evaluation, and hopefully that will make more sense. Yep.
So I think it's back to conversation, but that cluster that had taxis in it was always bad. I mean, even though they always chose taxis instead of the intruding word, since the rest of the cluster, the rest of the topics have been great, right? You can't. It seems like that doesn't allow you to differentiate between a topic that is all good except for one bad word.
Right. Yeah.
That's just totally garbage.
Right, yeah, and yeah, perhaps there's a better statistic that we could use to capture that. And so, like, you could look at the entropy of what people click on, and yeah, and do something like that.
Try to give them another option or something. I mean, because if taxis always looks the worst, they'll always pick taxis. But maybe you could give them like a multiple random subsets or something of the topic. Give them a chance for them to pick from a different set of words.
Yeah, that's a good suggestion. Where maybe you have like one intruder word and one deleted word, and just randomize those. Yeah, good point. Yep.
So, maybe for an interface tweak. So when you're going to say that two words shouldn't be the same topic, you could maybe pull up a couple of documents, highlight a bunch of stuff, and say, "Are you sure?"
Yeah, yeah.
I don't know if you've ever defriended somebody on Facebook. If you friend somebody, they'll show you pictures or even.
Oh, really? Wow. Huh. I did not know that. Yeah, yeah.
Related friends and stuff.
Yeah, so we did not do that just because it was hard to do that in our model because we didn't have the documents accessible at that point. But yeah, that's a great idea.
Yeah, that might look at Travis's recall question.
Yeah, and it would also address your question of, hey, there are documents where people talk a lot about bladder control issues and spinal cord issues. So, yeah. Yep.
You know, this business with spinal cord injuries and bladders and so on, it makes me go back to Ken's question, right? Because what you're doing is you're saying, here is some stuff, like, here are documents, cluster them in some way. And if instead of documents, I had, let's say, visual shapes, different colors. Maybe you're keying off on shape and NIH is keying off on color. That's why the clusters don't make sense to them.
Right, yeah.
So in that sense, I really think that if you really want to do this unsupervised, then I don't know if there's any sensible way of comparing with what people like. And if there is a way to quantify what people like, however badly, then you should regress on it and make a regression problem out of it.
Yeah, exactly. And I think there's some separable aspect to that. I mean, there's like, would this make sense to any human being alive, or would this make sense to person B? And so I think there's some sort of shared semantic issue, and then there's sort of like the customization. And I think we don't have a good handle on either of those.
Because Jason was trying to be charitable to us.
Yeah.
My attitude was, they're paying, so whatever cluster they want.
Yeah.
Well, or that represents expert knowledge.
Yeah.
Yes. No, that's what. There is something going on in their mind that keying off and stuff.
Yeah. Right.
And we try and capture it.
So I really like your shape color example, which is sort of related to the kind of topic levels that has been working on. It seems to me the best thing that we could do would be to discover all of the different attributes that are latent in the data at once by doing this kind of unsupervised learning, and then train regression, which is sensitive to those attributes. So that, once they link a few things together, say, oh, they're actually interested in smell. Okay, so let's give them clusters that are based on smell, not shape.
Yeah. Yep.
I'm wondering if this really goes.
Yeah.
I'm wondering if this really goes back to the debate between Chomsky and his teacher, Zellick-Harris. So Zellick-Harris believed in the distributional hypothesis, and the idea is that you can look at distributional statistics and maybe infer almost everything. Then Chomsky would say, there's almost nothing in the distribution, and then almost everything is somewhere else. And like meaning or in the head or innate hypothesis or on and on. And so there might be something that NIH believes for which the distributional evidence just doesn't apply.
Right, or maybe it would apply if you looked at the right data. If you had their email or something, then...
You're now taking Zellick-Harris' position. Chomsky would say
it
couldn't possibly be because the innate hypothesis has got to be right and the evidence can't be there.
Yeah, that's... I think that meshes with my philosophical standing.
What, the Zellick-Harris?
Yeah.
Okay.
Yep.
So you want to optimize these measures that you gather from mechanical then why not use them as a supervision?
Right. Yeah. I mean that is one way to do it. I don't think. So actually, there has been work on doing this. It's really slow and it's expensive, and so I suppose if NIH wanted to pay $100,000 for their topic model every time they wanted to run it, then sure, you could do it. And so, so Jonathan Chang has a paper called Not So Latent Dirichlet Allocation or something like that, where they actually have humans running as the Gibbs sampler and making these assignments. And so, yeah, you could do it. But there are probably... Right, yes. Fair enough. Yeah. And there are smarter ways you could do it too, but it would be expensive. But yeah, that is a good point. And that also gets to the sort of work that Chris is doing with machine translation and Blue versus actually getting humans to compare the scores. Yep.
So, I view this entirely as clustering.
Mm-hmm.
In that sense, there's kind of two complementary strategies that people often take, either a mixture model kind of approach or a hierarchical kind of approach.
Mm-hmm.
This seems to be basically a mixture model kind of
Yeah.
approach. Obviously, you could do a hierarchical kind of thing that would resolve perhaps some of the issues with spinal cord and bladder.
Yeah, yeah.
Thing, right? And then everybody can just say, okay, well, here's where I like to stop the hierarchy.
Mm-hmm.
That requires very little user intervention and basically code.
Yeah, I think that's a great point. And so then you need to figure out where, but maybe that question is easier to answer. Yeah. Okay. Thank you very much for the questions.